Oi, demystifying verbatim memorization in large language models. Cool paper here today. People usually assume these models can memorize a sequence they see one time in the training data set. Not true, kind of. And they assume that the memorization is very just like word for word, just matching up one-to-one relationship. In reality, they find here today that a lot of memorization is actually more so just the model doing regular language modeling with its own representations internally, like semantic representations working correctly, and that it's just the fill in the gaps part of the unusual, unexpected stuff that actually are one-to-one mappings, right? So, very cool paper out of Stanford here today. I enjoyed it. I think it's a good reframing and good evidence that the way we've been thinking about memorization in the past is not quite accurate. So, yeah, let's go check it out. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. So, when we say verbatim memorization, what we're referring to is when large language models output very long sequences of text that are exact matches of actual documents in the training data. Now, depending on your definition and what you care about, a long sequence could differ. For example, a lot of these big AI companies care about not copywriting. They don't want to be have these models output an entire New York Times article or something. So that could be one reason you care about this. Other reasons might be just performance, right? It's also pretty boring to think that, oh, are these models memorizing things that have been written before? We want these models to get smarter and come up with their own thoughts and have serious understanding. If they're just memorizing pieces of text they've seen before and not actually capable of combining concepts into unique combinations, into new sequences, then they're a lot less useful than just an internet memorizer, right? As far as why it happens, though, one hypothesis is that there are specialized model weights or mechanisms dedicated to recalling the verbatim memorized texts. Oftentimes, people assume that this is happening in the MLPs, the feed forward layers, right? The thought being here that whenever it sees a specific sequence of tokens as input, it's not actually thinking per se, it's not actually combining concepts in an interesting way that makes sense. It is rather just seeing that very specific sequence of tokens and outputting the memorized next sequence of tokens. This, I think I would call the prevailing idea in the field right now is that these model weights really can just memorize thousands or millions or whatever pieces of text very easily, despite being only a few billion parameters, and despite having only seen any given piece of text potentially just once. However, it could be the case that instead of using specialized weights or mechanisms dedicated to just verbatim memorization, instead of having these actual just rigid sequences memorized in there, it could be that models might be reconstructing memorized sequences using features learned from general language modeling. There's a big difference. If they're using their weights to verbatim memorize, it is a straight up direct mapping with no actual thought, no actual movement of concepts in representation space. Whereas instead, if they actually are reconstructing these sequences using features learned from general language modeling, that would mean they are, even though they're memorizing a bit, I mean they actually are using their thinking abilities, right? Their features in representation space. It just so happens that they have enough of these features or the right combination of features to be able to memorize certain sequences easily. That's a big difference there because in the first one, they are really doing the lamest version of memorization. That means they don't actually understand anything. Whereas in the latter, they actually are using concepts and whatnot, just combining them in ways that happen to be able to also memorize. Now, how do we go about actually testing this, right? Well, first off, we take a given model and its checkpoint at a given time during training, right? And using that checkpoint, not just the model itself, but we also preferably want the state of the optimizer at that checkpoint and the actual knowing the actual order of data up to that point and following. We can then split it up, copy it, and create two models, right? The control model continues training just regularly using the data as expected. Whereas on the treatment model, So control model we're going to call M naught, and treatment we'll call MX. On the treatment, we minimally alter the actual data set to include a set of sequences that do not otherwise occur anywhere in the data set. And beyond that, each sequence is then is repeated uniformly. So we actually have that given sequence not show up just once, this unique sequence, we actually have it show up multiple times throughout the rest of the training on this treatment model. Keeping in mind to make sure we have the same number of training steps, that it should be, rather than just being added in at those periods, it should be replacing whatever sequence was at that point in the total sequence of training data. Now, how are we defining memorization, right? Well, the verbatim memorization length of one of those injected added sequences is just the number of tokens in the longest memorized substring. So just any possible sub piece of the actual injected sequence, just whatever ends up being longest that the model can create. And we test them out by prompting the model with all substrings. So we just grab any possible substring in the actual injected sequences of length 8, 16, 32, and 64 tokens. So for a given added in there, injected and repeated sequence on our test model, we grab any substrings of those lengths and just put them into the model, see if the model will verbatim repeat out back to parrot to us the original sequence. And for how long will it do so? Will it only spit out the next 3 tokens or the next 50, right? And that is our verbatim memorization length. Keep in mind using greedy decoding, of course. But what does this data set look like? So they grab 100 sequences, each with 256 tokens from a piece of the internet sampled after the actual cutoff date of the original data set. Additionally, they don't just grab actual language data, they create a set of 100 shuffled sequences by randomly shuffling tokens in each original sequence above, right? So these first set, right, is a realistic idea of memorizing language modeling. This second set, or of just language modeling and data in general, this second set, because the tokens are random, they should not have the same patterns of regular language despite being the correct words for the distribution, right? Meaning, when we try both of these approaches, we try the actual just new sequences versus their shuffled versions. If we find that both of them are being equally well memorized, you would expect that means the models really are just verbatim memorizing things, are just not thinking at all, not using their inner representations, but rather creating strict one-to-one mappings of some prefix to the rest of the actual sequence, right? Whereas if we find that the models can memorize the correct language sample, but for the randomized tokens, the models are not memorizing them, that would mean that in the process of memorization, the models actually are pretty good about using pre-existing representations that are useful for general language modeling. They actually are maintaining their thinking structures when they memorize. So they are still mostly doing the whole thinking, the actual representations being used, and then just to some extent on top, it is easier for them to spit back out those sequences because they already have that baseline of representations being used correctly. Now, when studying these models, they chose a frequency range, a how often to throw into the data set these new sequences. They tested out many different ranges of frequencies, aka like, are we going to throw in these new sequences every 1,000 batches or every 5,000, 10,000, 100,000, etc. If they throw them in very frequently, for example, just every single batch, right, you would expect memorization would definitely happen. If they throw them in very rarely, for example, once or none at all, you'd expect no memorization. And what they found was that the range to actually choose, or the range that gave them a mix of memorized and non-memorized sequences, was about every 10,000 to 100,000 examples, which I believe means sequences in a batch as opposed to batches. I'm not quite sure though. And that was for a 160 million parameter model, so very, very small still, right? And in theory, a smaller model should have less capacity to memorize. Whereas when they scaled up to a almost 7 billion parameter model, they found that 94% of memorized sequences occur at least 1 in 5 million examples. So whereas the smaller model, 160 million parameters, needed the sequences to reappear every 10 to 100,000 times for it to kind of start being able to memorize, the larger model, a 7 billion parameter model, only needed to show up roughly every 1 in 5 million examples, which at that point, look at 1 in 5 million. If you go over to, for example, Andre Karpathy's Nano GPT repo, his replication GPT-2, one of the first big founding models, that I believe in his repo, he only trains on 10, was it 10 million tokens or a billion? No, I think it was billion actually. But still, this rarity of 1 in 5 million is so huge. Think about what happens when you have this keep scaling up to a 70 billion, 400 billion parameter model, right? It really raises the question, wow, you'd imagine that this 1 in 10,000 onto 1 in 5 million would move towards 1 in a billion kind of thing, right? It raises the question of whether a model might be able to memorize a sequence it has only seen once. If you have a very big model in a relatively small data set, maybe, or just a very big model, period, it might be the case that this rarity, this frequency of 10,000 at 160 million up to 5 million at 7 billion, that scale might keep going to the point where a GPT 4.0, whatever Claude size model might be able to just memorize a sequence it's only seen once. That's concerning, right? However, we just said that, but they went through and manually checked the actual low frequency sequences that were memorized with a 7 billion parameter model and found four patterns that actually created the illusion of a single shot verbatim memorization. So their original technique was automated, just checking for a number of tokens being repeated. But what they actually found was, in a lot of cases, that wasn't a great measure because of issues like templates with templated text where the variable content is usually provided in the prompt. These templates are actually so repetitive, it's not quite fair to say that their frequency is so rare. In reality, there's all over the place, right? Or a variation like spacing, punctuation, and textual variance of text is like, well, this isn't quite fair to say it's memorizing because in reality, it's just not a unique document. It's a very common document that just happens to be different in, for example, spacing, right? Or like text with inductive patterns, like ordered numbers. If someone has a web page on the internet that is just all the sequences of pi, so not even ordered, but just like appearing, or if it is a Fibonacci sequence, or even simpler, just actual ordered numbers counting out 1, 2, 3, 4, 5, right? Or repeating sequences, anything like cyclic at all, that would result in a very, very easy process to not even memorize. You could just use a single induction head to do that process. So it's not fair to say the model is memorizing in that case. And these patterns suggest that not all tokens in the verbatim memorized sequences are actually memorized. Some might be completed by the LLM in a reasonable manner because the text just is easy to complete. Their next finding was that the actual verbatim memorization length, the ability of the model to memorize and how long it can memorize sequences for, decreases significantly as the batch size increases, which, I mean, makes sense. With a larger and larger batch size, that one sequence takes up a smaller and smaller effect on the actual gradient. Whereas it may be the case that if you have a batch size of one, it might end up just working in a subspace that never gets touched again, and therefore just keeps going. And even after many, many training iterations, it's still able to memorize that text that it saw only once. However, in a batch size of 500, 10,000, whatever it is, right? The actual information conveyed from the one sequence onto the gradient is pretty low. And then even past that, when you look at how memorized that sequence is, and you just check every single time, like you have a given batch with a sequence in it, and then every batch after that, you stop the training after every single batch and just test out, is that thing still memorized? What they find is that the memorization length peaks around 25 to 100 steps after seeing the injected sequence. Not the first step. It's actually when you first step actually show that sequence gradient movement, like actually up to the model, right? It actually hasn't memorized it that well, it seems. You have to wait another 25 batches, 100 batches in until it actually has peakly shown its ability to memorize that initial piece of text that it saw a little bit ago, right? This is probably because of momentum terms in the optimizer. That makes total sense, right? Because really that actual sequence's effect on the gradient continues to affect the model throughout those remaining batches thanks to momentum. And to get specific with it, they found that with a batch size of 1,024 in pre-training, it's extremely unlikely that models with a size smaller than 7 billion can just verbatim memorize an arbitrary sequence in a single shot. So that's great to hear. Companies definitely are using larger sizes than that. I am still curious to see. To be fair, like This is only referring to single shot viewing of a given sequence, so reasonable, but like to be clear, memorization is still an issue in training because many internet documents show up quite frequently in the internet. Now, better language models are those that achieve lower perplexity on novel sequences drawn from their training distribution, right? On new sequences they have not seen before. From this perspective, we might expect them to be better at memorizing such sequences as well. Now, to decouple model quality from model size, they're going to do some experiments with three checkpoints at 1,000, 10,000, and 80,000 steps from the 160 million and 2.8 billion parameter models. So it's this steps that is the actual different quality here, I believe. And what they find is interesting. If you look at those results we talked about earlier with how long it takes to memorize and the actual peak memorization length and everything, what they find is that later checkpoints, so that step 80,000 as opposed to 1,000, later checkpoints actually memorize more. And the larger model is able to memorize more even when seeing the sequences fewer times. So if a given sequence showed up very early in training, the odds it's memorized are very low, not just because it has seen so much gradient info since then that's been overwritten, actually because earlier models or like worse models, like models that are earlier into training their training run, are just worse at memorizing. Very interesting there because you wouldn't expect that if the model was literally just finding a certain subspace to one memorize verbatim that sequence. Rather, this kind of implies that the model is using representations and internal algorithms that it has learned that are good for general language modeling throughout training. So the reason that a further into training model has a higher chance of having memorized a sequence 25, 100 batches after it saw it is because it actually has more internal structure, more internal representations that are useful and good for general language modeling. Now, if memorization did work in the verbatim one-to-one, just using some tiny subspace or something idea, then one hypothesis would be that outer domain sequences. So, for example, maybe you trained entirely on internet text, and this was, well, no, maybe you trained all on scientific text, and now you're doing creative writing or something. Anyways, outer domain sequences are more likely to be memorized as they contain rare sequences of tokens that can be used as identifiers to recall memorized content. So, if a sequence is out of domain, meaning it is very, very different from the rest of your training data, then you would assume it has combinations of tokens that are otherwise not seen, that if used as a prefix, as a prompt, would be a clear indication to the model, oh, this is that one sequence I saw the one time, right? Whereas the other hypothesis is that in domain sequences are more likely to be memorized because they have lower perplexity before training. So their model's already good at modeling in-domain sequences, therefore it should have an easier time at memorizing in-domain sequences because it can reuse its representations that it already has in part of that memorization. And what they found was the latter was the case. On average, the original sequences drawn from the training distribution are in fact more likely to be verbatim memorized than shuffled sequences, which are outer distribution. And again, this points towards the idea of the models are not just getting specific mappings of one-to-one memorization that are useless and meaningless. They actually are using their internal representations and algorithms as a kind of foundation for the little sprinkle on top, which is memorization. So what's happening here is much more complex than just recalling a sequence based on some unique identifiers, as otherwise we would see the models memorize more shuffled sequences, more outer distribution sequences. If it was so simple as just like, oh, unique order of tokens there for memorization, then we would expect that to actually work with outer distribution data with shuffled tokens, but it doesn't work. It really only works with regular in distribution language to be memorized. And this kind of reminds me of when someone has an idea and really that idea is not original. What happened is they heard it somewhere else and then just kind of forgot it. You're kind of, when you have that like repeated idea, you're kind of reusing your memories a little implicitly. You just don't even know it yet. And that kind of reminds me of that here is that the model is reusing information it already has to do said memorization. Now, next question is which tokens encode the information of the verbatim memorized sequences, right? Or do models encode token level information at low level representations or more abstract states of the model, so high level representation. So when we see the actual memorization happening, Does that memorization happen at the level of the actual token embedding vectors, or just very, very early layers, or does it happen at more abstract states of the model higher up? Does the model have to actually use general language modeling algorithms to create information first, and then once it has that constructed, it can then recognize a sequence as one that it has memorized, is the question here. So if we look at our treatment model, the one that actually has received sequences to be memorized, right? It takes as input some prefix, which is just a sequence of tokens, and you expect if it has memorized that sequence, then the whole sequence, then you expect for the prefix, it will then output the rest of the sequence. So that prefix P creates an internal state in the model that is sufficient for generating the rest of the sequence. If verbatim memorized information is localized to the trigger P, then every token in the rest of the sequence should have a causal connection to the internal state of the model, right? So if we look at this model, but we replace representations at a given location, a given part of the sequence with different values, then what can we expect to happen? Well, when you do that, when you actually replace the internal representations of the model, you find that not all tokens in the verbatim memorized sequence are causally dependent on the trigger representations on the actual tokens. Instead, these tokens that are outputs, the memorized sequence, often exhibit dependency that resembles syntactic structures. For example, the direct object depends on the preceding verb, or the closing parenthesis on the opening parenthesis, meaning that when we take our prefix and then our memorized output, when we remove certain parts of the prefix, we do see causal relationships, whereas other parts we don't. So if you were to remove that opening parenthesis, you would see that the closing parenthesis never shows up. Whereas for sequences with no clear structure, memorized tokens depend on more trigger tokens that are relatively rare. So it more so depends on all of the tokens rather than just like the obviously syntactically meaningful tokens. So whereas what they found was that most memorized tokens depend on higher level representations produced by middle layers. So it wasn't the tokens themselves, it was the later down the calculation line after the model's already done lots of thinking, representations in middle layers that actually result in the repeating of said memorized tokens. Meaning that information about the verbatim memorized sequence is, first of all, distributed across tokens, and second, encoded in abstract states as opposed to token level features. There is simply no representation of the trigger, P, the input prompt, that causally encodes the entire memorized sequence. Moreover, the fact that not all verbatim memorized tokens are causally dependent on the trigger suggests that the model might only memorize information about a subset of tokens and fill in the gaps with the general language model. So whenever the general language model is good enough to actually just know what to say next, it just uses that. And then with the gaps, with the unusual things, the remaining weird parts, that is when it might be using regular just memorization. The verbatim memorized sequence might not be actually fully memorized, it might be reconstructed token by token, where each token is predicted using different mechanisms depending on the structures involved. So if they have structures that are very clear, obvious to the general language model, it'll use those. If they don't, then they might do some actual one-to-one mapping memorization. And this would explain why in-domain sequences are more likely to be memorized, right? Remember earlier, in-domain regular language versus like shuffled sequences? If memorization was actually a one-to-one mapping with no actual understanding or meaning, we would expect that randomized sequences we memorize just as often. But what we have actually found is that the sequences have to actually look like and be English in order for this to work, for the thing to be memorized, because the model actually is using its general knowledge of the human language when repeating said memorized info back. It is mostly using its understanding. Only for the small, random, weird gaps is it actually just one-to-one mapping memorizing. So now what they're doing is they're taking that base model that was never given the repeated sequences to get memorized, and they're seeing if they can do an intervention that controls that model and makes it produce memorized strings by throwing internal states in there from the treatment model from the actual one that did experience these memorized sequences. And now, to be fair, there probably was some degree of drift between these two models as they kept training. But remember, the only difference in training was occasionally like 1 in 10,000, 80,000 tokens, whatever it was, replacing that 1 in 80,000 sequence with the one that is being repeated, right? Whereas most of the actual training should be the same. Um, if the models were to diverge a huge amount, that'd be an issue, but they should be similar, right? Roughly. They started from the same checkpoints and they kept going with 99.999% the same data, unless the system is really chaotic and sensitive to dependence, which I guess it could be. Then you'd expect that these representations internally should be somewhat transferable. Now, the core finding is that while these interventions of taking the memorization model and its internal states and throwing them into the base model do not lead the base model to produce entire memorized sequences, we can get it to produce the first few tokens of such sequences. Moreover, among the interventions at a layer that do produce memorized tokens, more than 50% can still produce the same memorized tokens using model components at the corresponding layer from the base model, which are weights learned only from general language modeling, meaning even the base model is capable of repeating the actual verbatim sequence tiny bits because it is using general language modeling, which is good enough to just know what to say next, meaning that the actual memorization model is using those things as a base as well, those internal representations as a base for how it does things. And when they went to actually quantify this effect, they found that a quarter of the verbatim memorized tokens result from general language modeling. So that's your rough ratio. I'm not quite sure how they got that. I read this a while ago, but apparently 25% seem to come from just general language modeling circuits. The other 75% might be actual full-on one-to-one mappings. And they also confirmed that the actual treatment model, the one that was being given sequences being memorized, is in fact performing similar computations when you look at the actual MLPs and everything as the original base model, which of course are computations learned for general language modeling. Now, there are a few places, such as the MLP in layers 1 and 3 in one of these models, or attention in layers 1 and 4, which are significantly different, suggesting that these components might have actually diverged in the two models, whereas most of the layers, most of the MLPs and attention matrices are actually the same. And the ones that have diverged presumably would have stored memorized information. And the fact that they found it was relatively early layers, 1, 3, and 4, that were actually diverged as opposed to later layers, does line up with previous work that uses gradient based approaches to indicate that, to show that lower layers do in fact play an important role in memorization. So one would hope, and there's a whole fields of trying to avoid memorization and everything, one would hope that we could find ways to identify and control memorization. However, the findings of this paper suggest that such control may be hella difficult to achieve because verbatim memorization is thoroughly intertwined with general language modeling. This intertwining means it might be so hard to actually remove this as a phenomenon from language models. Now, if you want to find a good method on how to remove it, actually, I have a video that came out probably a month or two ago at this point that I will link in the description and probably show as a final on the screen when this video is over. That will show you a method. I think it's called goldfish loss or something. But anyways, check that video out if you're curious as to how to remove or prevent models from memorizing. It does come at a cost to some actual training compute, to be fair, but other than that, it is pretty cool. And keep in mind in the future when discussing this topic, these findings suggest that verbatim memorization is something of a misnomer, as the phenomenon involves memorization of more abstract model states, for one thing, as opposed to only memorization of token level information, and also a lot of it isn't even memorization, it's just general language modeling, right? So when we use that term in the future, be careful about it, be very clear, like this old idea of, oh, the model just sees the sequence one time throughout training and hasn't memorized, not quite right. Now, the fact that these models memorize at the level of abstract intermediate layers and states, as opposed to just simple token sequences, raises the concern of whether focusing on verbatim memorization reveals the full scale of what models actually memorize. Remember, with plagiarism, right, you don't actually have to repeat word for word. Even pretty obvious paraphrasings do still count. And LLMs could memorize long sequences of abstract states as well, of abstract states, which might remain undetected if we only focus on verbatim memorization. When in reality, these models might frequently be using different words paraphrasing, but the same rough answer to the same input prompt, right? There's actually plenty of previous research about models memorizing syntactic templates where the actual words are different, but roughly they said the same things in the same order, right? I had a paper recently that I read um, talking about how reinforcement learning from human feedback actually heavily encourages that. I'll link that one down below as well. And it actually that is actually a difference between the initial training phase of pre-training versus the actual post pre-training phase of the alignment phase, right? That's a difference there, where the alignment phase actually introduces syntactic templates as well. Don't leave yet. If you got this far, you're going to love this video or this playlist. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.